everybody knows Guy. Half the people here probably know Guy. The other half will be happy they know Guy. Guy works as a developer evangelist. If you'd like to know more about what they do, there's a YouTube channel with Guy talking about a YouTube video about Guy talking about what he does as a developer evangelist slash advocate and what he doesn't do. Guy has been a coder for how many years?
25 plus.
And you most likely met him at a company called Pillar. Is that fair to say?
I was there for 5 years.
Yep. Is there anything else I should add? He lives in Columbus, Ohio, not Michigan, but we'll forgive him for that.
Yeah, it is what it is, right? I'm not from Columbus, so I don't care about the football thing.
Yeah, and they canceled the game this year because Michigan didn't want to lose.
Yeah. I grew up in Northern Ohio watching the Browns lose, and so I don't watch football because it was painful.
So is there anything else, Guy? Anything else interesting to know about you?
I don't think so. But I have a slide where I'll talk all about me.
Yeah. And how would you like questions? I know you like to answer questions.
So we got a small group here on Zoom. If you've got a question, just ask me. Just unmute yourself and ask. I'll be happy to answer that question. And if you want to put it in the chat, I probably won't be watching the chat because I'm going to be busy on my slides and everything else. But if Joel, if you see a question come up in chat or on chat on like YouTube or Twitch or one of those, feel free to pause and interrupt me, and I'll answer the question to the best of my ability.
Interrupting people. See, it worked.
Yeah, you're perfect at it, right? It's that right there is a talent. Don't hide that in a bushel basket.
Ask my wife how much I practiced.
So I'm going to go ahead and share my screen here so we can kick this thing off. We'll share desktop 2. And there you can see a very boring Mac screen. And then we will present a slide. There we go. Can everyone see my screen? Excellent. So welcome to Mystery Machine Learning, Jinkies. Here's my little intro slide. Guy Royse, developer advocate, Redis Labs. Probably the most valuable line on this slide is this one right here that says github.com/Guy Royse. All the code for all the stuff I'm going to show you tonight is going to be out there on GitHub, and there'll be a link to it later too, so don't feel like you got to grab it. You can follow me on Twitter at Guy Royse if you're so inclined. I mostly just post updates about things that I have going on, and I'll post things that I think are funny, and that's about it. And I'll occasionally troll people that I know in responses. And if you want to read my out-of-date blog, that's at guy.dev. So that's me. A very important fact about me that's relevant to this talk is summed up in this initialization here. It's not an acronym because you can't pronounce it. Well, I suppose you could pronounce it, but it wouldn't be safe for work then. But this initialization is an important fact about me relevant to this talk. Any ideas of what it might stand for?
I am not a something.
Yep. I am not a
developer.
Data scientist?
Data scientist. That's correct. I am not a data scientist. I'm going to do a talk on data science, but I'm coming at it as a fan of data science. I'm a developer. I think like a developer. I don't have a heavy math background, and so I try to take the machine learning concepts and turn them into more intuitive things that I can share with everyone, which I think is useful. And as a developer, it's more how to use these tools, right? So what I do is I go out and I figure out how to do stuff with these various machine learning tools and data science tools, and then I do something, and then I share what I've learned. There are other ways to solve these problems. I don't know them all. I'm basically saying I'm not an expert. And partly I'm not an expert because I hate the phrase expert because it says so much, but it doesn't say anything at all. But also in this particular case, this is, I don't have the years and years of math training to be a data scientist. It's a hard profession. I'm a developer that plays with data science and shares stuff. So that's my little disclaimer at the beginning of my talk. In addition to not being a data scientist, I am a big fan of Scooby-Doo. Well, probably more fair to say I was a big fan of Scooby-Doo. I mean, I'm 48 now, and so I don't really watch Scooby-Doo like I used to. But as a kid, I enjoyed Scooby-Doo thoroughly. And you know, the thing with Scooby-Doo is they always had a mystery to solve, right? And it was always just some man in a mask that was the secret ghost behind everything. And that mystery that they needed to solve, well, I want to solve a mystery too. And our mystery is identifying who said what. Was a line or a quote, which member of Mystery Incorporated would that quote be credited to? You know, someone says Jinkies. Well, who is that? That'd be Velma, right? If someone says, "Hey gang, let's split up," oh, that'd be Fred. And you know, if someone goes, well, then that would be Scooby-Doo, right? And so what I'm going to do is we're going to build a machine learning model or recurrent neural network that you can type these lines into, and it will tell you who said them. And it'll be doing natural language processing to figure out, even if you have words that the model doesn't recognize, like if you bring stuff in from the SpongeBob universe into Scooby-Doo in your things you wanted to make a prediction on, it will still work. So it's not just a database looking these lines up. It's actually trying to understand that language and make a prediction. In order to do this, I've got a data set of all of the lines that Shaggy, Scooby, Daphne, Fred, and Velma say from various movies and cartoons. So someone went out, got all these scripts, built a data set. The data set is literally, the first column is a CSV file. The first column is who said it. And the second column is what they said. That's the data set. That's all the data we have to train this thing with. We're going to use that data to build a neural network that will tell us who said it. And we're going to take that neural network and we're going to deploy it onto Redis using RedisAI. And then we're going to build an application that will use that model that's in RedisAI to make predictions and tell us whether it's you know, Daphne or Fred or Scooby or Shaggy or Velma that's said the thing. So that's what we're doing tonight, which I think is kind of fun and ridiculous. Topics we're going to cover in doing that is we're going to look at neural networks, and I'm going to look at neural networks in detail so that we can kind of get down to a first principles sort of view of it. Maybe not all the way down to first principles, but we're going to look at neural networks down at how they work at the neuron level. And then you can see how they aggregate together. And then we're going to look at recurrent neural networks, which are particularly a variety of neural network that are configured in a particular way that makes them good at dealing with time series data. And then we're going to look at how we can build both of these types of neural networks using Keras, which is a Python library that's part of TensorFlow. That's sort of like a DSL for a domain-specific language for building neural networks. And then we're going to look at how we can take these models and put them on RedisAI and wrap them up in an application. My clients are in JavaScript, but you know, you could use any language you want. So that's what we're going to build. So let's dive into what are neural networks first. So this is a picture of a neural network that you've probably seen before. If anyone has touched machine learning type topics at all, you've probably seen this sort of basic picture. And what it's showing here is an input layer. So we got a bunch of X's coming in, input layer. I did them zero-based because I'm a programmer and not a data scientist. If I was a mathematician, these would be X sub 1, X sub 2, 3, and 4. But I wanted to be zero-based. But so we got this input layer. We got numbers coming into this neural network. And each of those input bubbles represents a single number coming in. We got a couple of hidden layers. So all those input layers, then the outputs of those go to the hidden layer, and all the outputs of each of those hidden layers goes to the next layer. And you can see that it's fully connected. So the output of, say, this neuron right here goes to every single neuron in the next layer. And then we have an output layer, which has 3 numbers as output. And so this is sort of, you can think of this as a function. It is a function. It takes inputs, it transforms them in some way, and it creates an outputs or outputs. And this is a function not just in the programming sense, but really more in the math sense. Where you put X in, you get Y out. And so functions like that in math are responsible for drawing lines. And so this function will draw a line. That line can be all kinds of shapes. And we can use those lines for a couple of purposes. And technically, this isn't a line. I'm showing it as a line because it actually fits on the screen that way. But depending on how many variables of input you have and how many variables of output you have, you're actually creating a hyperplane that bisects a space. And so in this case, our hyperplane is a line, which is a one-dimensional structure, bisecting a two-dimensional structure, which is the space. But you could have a plane bisecting a space, a three-dimensional space. You could have a five-dimensional hyperplane bisecting a six-dimensional space, et cetera. So, those are hard to visualize and hurt our brains. So we just do two-dimensional stuff. And so this line can, like I said, bisect this space. And so you can use that line to classify. You could say, is this thing on this side of the line or the other side of the line? Is it a hot dog? Is it not a hot dog? And, so you put in your data, it plots a point, and you say, I'm on the southeast side of the line, not a hot dog. I'm on the northwest side of the line, it's a hot dog. Scoob, not Scoob, right? So that's one way. This is called classification. And so you can take that line being drawn by that neural network and use that to do classification. You can do this with other types of machine learning as well. The other thing you can do with that line is you can plot a point on it. And instead of getting a class, is it this thing or this other thing, you can instead get a value. And so here we have a little graph that's showing the number of Scooby snacks required to get Scooby or Shaggy to do a thing based on the spookiness level. And so, many times in the show, it's like, would you do it for a Scooby snack? Right? And then, so the question became, well, would you do it for 2 Scooby snacks? And here we can see that clearly this regression line shows us, that at this point, a spookiness level of 2 would be met by 2 Scooby snacks. So 2 Scooby snacks would be enough to get Scooby to face a spookiness level 2 challenge. And this is called regression. And instead of providing a category, it provides a continuous number. So at any point along this line would work. Now, this is a real simple one, obviously, and it's saying 1 Scooby snack for a spookiness level of 1, 2 for 2, 3 for 3. And so it's real simple, but this line could be much more interestingly shaped. It doesn't have to be this simple. And again, it doesn't have to be two-dimensional. You could have 10 variables, and then all of a sudden you've got this line that's being, or this hyperplane that's being drawn through all those dimensions. So that's kind of what a neural network does, is it draws these lines and then lets us determine whether this is, do classification or do regression. And so let's break down the neural network and look at a single neuron. Here we have the simplest neuron possible. It has a single input, X, and a single output, Y. And so this is not a realistic neuron because neurons usually have multiple inputs, but we'll start here and then we'll expand. And so if you say it's got input X, output Y, that's going to draw a line, right? If you plot that out, for X, what's the location Y? For X, what's the location Y? And you can plot it out. Inside of this neuron, to help it calculate, to draw this line, it has a weight. And what we do is we multiply that weight times the input. So X times W. And it has a bias, and that bias is added to that multiplication. And so this is how it computes the value for Y. And if you're paying attention, we could express it algebraically like this, where there's our input, W is our weight, we add a bias of B, and that yields an output of Y. And if you're really paying attention, you'll notice that this is actually Y equals MX plus B, which you probably remember from Algebra 1, right? It's the formula for drawing a line. You got the slope, you got the Y-intercept. The Y-intercept is the bias, the slope is the weight. In fact, I think it's kind of funny because you turn the W upside down and it actually is exactly that formula. So it's, so obviously that it's kind of funny. And so what it means is a neuron like this basic neuron draws a straight line. That's what they do. They draw straight lines. And those lines could go lots of different directions. They could have different angles, and that's what the slope and the bias do. Or the slope and the Y-intercept do. And so, it draws us some lines. But that's not always what we want. Like if we had a layer of straight lines being drawn, and then it feeds into the next layer of straight lines being drawn, then we're just going to get another straight line, which means that we only get straight lines out of our neural network. And so we need to do something to change that output in that neuron. We need to make it less linear. And we do that with an activation function. And so if you think of the entire neural network as a function, now it's made of smaller functions, and that smaller function has a function inside of it. So it's, it's like matryoshka functions. And so that activation function can be a couple of varieties. There's lots of choices here, but there's really the one that everyone uses. So a couple of the choices are sigmoid. So this can take your line and turn it, that number that's output, the y value, and turn it into a value from 0 to 1. Approaches 1, approaches 0. If your value is 0, it hangs out at 0.5. And then it goes up and it goes down. So you're getting that number that approaches 1. It flattens it out. It narrows it down. Another one that is popular is a hyperbolic tangent. It's pretty much the same thing as a sigmoid, but taller. And instead of hovering around 0.5, it hovers around 0. And then it approaches 1 and it approaches -1. It doesn't reach it, but the bigger the number, the closer it is to 1. But the one that's used the most, and actually the easiest one to explain, is the rectified linear units, or ReLU. ReLU is a fancy way of saying max 0, x. So if for x, a particular value of x, if it's 0 or more, it is what it is. Otherwise, it's 0. So if I go to 5, ReLU spits out a 5. If I give it a -1, ReLU spits out a 0. And this is by far the most, I'm going to say by far the most used function in activation function in neural networks. It just seems to work really well. I'm sure there's a mathematical proof that shows you why that works. I don't know. I just know that it works when I use it. So, so that's one way of transforming it. And so then you don't get a straight line anymore. You get that line like that from a neuron. And these real neurons aren't taking one input. They're actually taking multiple inputs. So here we've got multiple X inputs and a single Y output from this particular neuron. And again, we've got the weights and we've got the bias, and we multiply the weights times the inputs, we add the bias, run them through our activation function, and we get a Y. And so it looks like this. X times W plus X times W plus X times W plus B equals Y. And this is drawing that hyperplane through that space. And to express it a little more mathematically, we can say it's the sum of the inputs times the weights plus the bias. So that's sort of a neural network at the lowest level that I can effectively describe it. Once you have that neural network, then you can see that's what's happening inside of all these. So you're drawing these kind of crazy shaped lines, these ReLU-ish lines, and then those values feed into the next layer, which feed into the next layer. And all of a sudden, the lines that you get out of the neural network aren't straight anymore. They're all kinds of curvy, interesting stuff. And it allows you to make interesting lines to do interesting classifications. And so this is a simple function that I wrote to draw some little lines. I just used the grapher tool on the Mac to do this. But and so you can start cutting that space up and classifying it, or you can start regressing on it. So it's all about drawing interestingly shaped lines. That's really what machine learning does. So one thing about these types of neural networks that I've just explained, though, is that they actually, they suck at data that has any kind of chronology to it. Right? So if it's got some sort of this happened before this and this other thing happened after this, if you could build a neural network and say, I want to put in 10 words and I'm going to turn them into numbers somehow. And then you tell me words out. But it doesn't know which words actually come first. There's no order implied by the structure of the neural network. Recurrent neural network provides that order, that time series nature. And so they're good for things that have time series data, like you could do it for like stock market predictions, although I have some questions as to whether that is very effective. If I could do machine learning to predict the stock market, I wouldn't be talking to you about machine learning. I'd be predicting stock market and retiring early.
Yeah, we had this conversation once, and what I remember you telling me is the moment you optimize for a pattern, the pattern changes.
Yeah, I think it's called a level 2 complex system or something like that, where the prediction of what the complex system will do when utilized changes the system. And then there's other types of complex systems where you can make predictions, but acting on the information doesn't actually change the complex system. The stock market changes when you modify your behavior as a result of making predictions against it, which ultimately drives the stock market towards greater efficiency. And then everyone does it, and then everyone just has to do it to compete. and then you're back where you started.
Versus a complex system.
What's that?
Like the chaotic system versus the complex system.
Yeah. I've seen a couple different terms. I saw one, it was like a level 1. They called it a level 1 and a level 2 one time. But yeah, chaotic versus complex is much, much better. And probably what smarter people than me say. So, but a recurrent neural network's good at that. And one of the things that's sequential data like that is language. And so recurrent neural networks are good for doing that. It has an input layer, just like a regular neural network. Has an output layer, just like a regular neural network. And these circles here can be, I'm going to say for now that they're individual float values, but we'll see that they'll turn into actually input layers as opposed to just an input itself. So like x sub 0 is actually has many values coming into it. And then they've got hidden layers, just like a regular neural network does, but they're a little different. These hidden layers are totally just a hidden layer, just like in the previous network. But what we do is we take this first input and we run it into that hidden layer, and it generates an output. That output goes into the next layer, providing the context of the inferencing that happened from that first word being put in, that first bit of data from the time series. And then this layer takes that previous computation, that previous result, and takes the next thing in the sequence, and then uses those two things to make a prediction, which goes into the next layer. And so the neural network gets that sense of temporality, and it gets that context of the previous words or the previous data. So it can find patterns that go over time. And then eventually we'll go ahead and output these things. And we can output multiple values or a single value. There's lots of ways to configure these. But the thing that makes the neural network different is it's still neurons connecting in exactly the same way, but they're wired up differently in a way that provides knowledge of the past. You can set these up in a many-to-many arrangement where you put in multiple values and you get multiple values out. A classic example of this would be for translation. So you put Shaggy saying something in English on one end and Scoob says something in Scooby speak on the other end. You can also use these for chatbots. So this would be an example of the Scoob chatbot. Shaggy says, "Look out, Scoob. What would Scooby say in response?" Well, this could predict what Scooby should say in response. He would say, "Okay, Reggie." And so there's that many-to-many structure. That's one way of doing these. Not the example we're going to do tonight, but it's one way of doing them. Another structure you can do is you can do a one-to-many. One-to-many takes one input and then generates multiple outputs. And so it doesn't have the context of necessarily the input history, but it has the context of the previous things it's predicted. And so with this, probably the best use case for this is image captioning. And so this input layer could be the result of a convolutional neural network. And then it could look and see what things are in that image and then caption it and tell you what's in it. You could also use it to generate text, but if you say something that Daphne would say, it would just always say the same thing. So it's not nearly as interesting. But maybe we give it a picture of Daphne and it predicts that she would say, "Jeepers, they mean business." But it's taking a single input and then generating multiple outputs. And we got the one we're going to use tonight, which is the many-to-one. And in the many-to-one, you can take multiple inputs, you get a single output, many-to-one, right? This is great for sentiment analysis. So you give it a line and it spits out a number saying, is this a positive or negative review on Amazon? You can do it for predictive text. Given these words that I've entered so far, what would be a good next word for me? That also works with many-to-many. I can say, here's all my words. Give me 3 words that I'm likely to say next. For what we're going to use it for, we're going to do text classification. So take this text and put it into some sort of classification, some category, some bucket. Our example is going to be who said it, Shaggy, Scoob, Daphne, Fred, or Velma. Hey, let's split up. That would be Fred. These buckets could be things like, I've read the context of this email and we're going to route it to the collections department versus the customer service department versus the level 2 support or whatever, right? So you could do lots of things to classify this text. And lots of practical uses for this pattern as well. We're going to do the impractical ones today. So we're going to look at how we're going to classify text. We're going to classify something that Velma says. Velma is always saying, I can't see without my glasses. That's sort of her thing. And when we look at this, I'm showing a picture of Velma as the output, and I'm showing text as input. But machine learning models, deep learning models, neural networks, none of these things actually work on text. They work on numbers. And so we need to turn our input into numbers, and we need to turn our output from numbers into a class. And so the way we turn our numbers into words is using a thing called tokenization. And so we start with our data set. Here we've got a data set of 24 words from this corpus of text. We've got Jeepers and Raggy Relp and like, step on it, Scoob. These are all words. And we know who said them. But we're going to take that corpus of text, all the lines from the Scooby-Doo data set that I have, and we're going to turn them into, basically an index. So we count them all up, putting the most populous common words first and the least common words later in the list. And we just give them an index from 1 to n. So we've got 24 words. Like is the most common word. Well, like and Raggy are both the most common word, but like is alphabetically first, so I put it first. And so that gets an index of 1, Raggy gets an index of 2, Glasses 3, all the way down to Zoinks with a 24. And this is, now each of these words can be numbers. This is really no different than the substitution cipher that you used to use when you were a kid. So if we take our little substitution thing here and we want to encode the word I can't see without my glasses, we look I up on the list. It's got an index, a number of 10. So it's 10. And can't is a number 8. And we just map it out and we get a little vector that contains these words. We've taken these words and turned them into numbers. This is like doing A equals 1, B equals 2, C equals 3 to encode a message when you were a kid. Same idea, slightly more advanced. One thing you might have noticed is that this example had missing words, right? So there's not a word there in the first input. And so we have a null there. And the neural network requires us, this particular example requires us to input 7 words, but we only have 6 words. And so we have a null. And so what we do is we map that null. You'll notice that null isn't in here. You'll also notice that I started with a 1, and I made a joke earlier about being a programmer, and I always start with a 0. And well, that's because the null gets the 0. So if there's not a word in a position, you get the 0. Or if the word's not in the dictionary. So if we build up these words and then we give it a word it's never seen before, like spectacles. We've got glasses, we don't have spectacles. Then spectacles gets turned into a 0. So this is the way we sort of handle things we don't recognize and the way we handle things that just aren't needed. And we always right justify our words because it's temporal, right? The leftmost stuff is the oldest stuff. And so we, the further in the past the data is, the further to the left the data is, the less important it will be to the recurrent neural network. And so we want everything to push everything to the right. So if this is in our real example, I think my input width is 150. So you get padded with a bunch of zeros and then just a few words at the end for most of our examples. Once we do that, once we've got that list of words, this is I can't see without my glasses, null, I can't see without my glasses. We now need to one-hot encode these. And so instead of each input on the recurrent neural network just taking a single value, they're actually going to take a vector. And that vector is going to be full of zeros and have a 1 for the particular word. So one-hot encoding says word 10 is position 10. It's the word I. Put a 1 there, everything else is 0. Word 2 is can't. So put a 1 in can't, put 0 in everything else. So we're one-hot encoding these. So these arrays now would be going into the input on the neural network. Except that's not actually what's going to come in next, because we want to do another thing to, like if we have a dictionary 10,000 words, that means we have a lot of inputs and they're mostly zeros. And so there's this idea of word embedding. And what word embedding does is it creates a matrix of words to look up. So here we have this big matrix that is 6 wide and it's as tall as the number of words we have. And the numbers in here sort of encode the semantic meaning of the meaning of that word. So words that are more closely related in meaning will have larger numbers that are the same. So like glasses here, we have a 75. If spectacles were in our set, that's a very similar meaning to glasses. And so spectacles would have a large number in this column as well. Whereas a smaller number in this column would mean it's not as related to that concept. So these columns sort of end up meaning sort of semantic categories. And the bigger the number, the more this thing fits into this category. It's showing how closely related these words are in concept. And I know that Keras takes care of this for me. I don't actually know how it builds this matrix. I know I tell it to build it and it does, but I don't know what it's doing internally to make that happen. So, but what we do with this matrix is we take our one-hot encoded word and we find the row that matches it. So glasses is our one-hot encoded value. And so we get the row that matches that. And so this 1, 2, 0, 14, 75, 0 is now, this row is now what's input into our neural network for that input. So if we look at this, now we'll see that null is all zeros because there's nothing there. I is 102. And if we go back to the previous slide, you'll see that, well, I don't know if I did it. There's glasses. We'll look 1, 2, 1, 0, 1, 14, 1, 2, 0, 14, 75, 0. So that row gets put as the input for the word glasses. My gets input right here, et cetera, et cetera. So we're doing a lookup and that becomes our new input. So this is what actually gets put into this neural network. What's really being output is not Velma. What's being output is instead a vector of numbers equal to the number of classes we have. So we've got 5 values being put out here, and they should add up to 1. And each of these 5 values corresponds to one of the members of Mystery Incorporated. And so we take the largest value, and so the model is 83% certain that that's Velma, 11% Scoob, et cetera, et cetera. And so this is how we take those numbers and turn those back into classes. So that's pretty much all there is for how recurrent neural networks do what they do. One important thing about this, and I hinted at it earlier, is the vanishing gradient problem. So what happens here is, I mentioned how this input here is this box right here, right, is made up of the previous results and the current input. And things in the past become less important. But that's not always true, especially with natural language processing. Just because the word's first doesn't mean it's less important. And so, but what happens with a recurrent neural network is all the way here on the right, this last hidden layer is taking glasses and it's taking the result of everything that came before it. And the result of everything that came before it is half of the decision process. And glasses is half of the decision process. And then my is half of that. And so words that are way, way, way back at the beginning that might be really important don't have as much weight in determining what our output is. And so I'll be able to show this once I show the model, because I can put things in I'll put in things like I can't see without my glasses, Scoob, or I can't see without my glasses, Scoob. And that last word, Scoob, tends to mean something Shaggy says. And so even though Velma would most likely be the one to say, I can't see without my glasses, Scoob, that Scoob is overly weighted. And so this is a flaw with this basic recurrent neural network. The solution is to use some more advanced recurrent neural networks. There's the LSTM, which is long short-term memory, and it hangs on to things that it thinks are important. And I don't profess to know how these work. I haven't researched them in detail yet. Gated recurrent unit does something similar using a different mechanism. But it's the idea of trying to, in essence, the recurrent neural network has only short-term memory. And so these are trying to give it some long-term memory along the way so that it can have some context that it can hang on to how important a word is or might be. So those are things to go research if you want to go deeper into this topic. We're going to look at Keras next and how we can use Keras to build a recurrent neural network and just a regular neural network. Keras is a domain-specific language that makes writing neural networks really easy. So you're not doing a bunch of math. You're saying, give me a layer with this, and give me a layer like that, and give me a layer like this. And so you're just specifying, you're talking in terms of the neural network itself. It's written for Python developers. It's a Python library. And it's part of TensorFlow. It wasn't originally, but it was incorporated in TensorFlow. And so to define a simple neural network, this would be the sort where I showed at the beginning, the full feed forward neural network. The first thing we need to do is create a new model. It's called a sequential. And it's called a sequential because it's a model that's made up of a sequence of layers. So it's got this layer, and then it's got this layer, and it's got this layer, and this layer in sequence. So that makes it sequential. We will add a layer. We'll say model.add. We'll say we want a dense layer with 5 neurons. Make the activation function out of those neurons ReLU. That'd be the max 0, x. And go ahead and specify the input shape as well, which defines our input layer. The input shape is 4. It's 4 comma, so that Python knows it's a tuple. You can have input layers that are multidimensional if you're doing like image classification and stuff like that. And so these define our first 2 layers. Then we can define another layer, dense 5, activation ReLU. Define our output layer, also a dense layer, dense meaning fully connected, with 3 neurons. And then this has an activation of softmax. Softmax takes the numeric outputs of those 3 neurons and makes sure that they add up to 1 proportionally. So just like with Mystery Inc., we had the 5 members, we got 5 numbers out, they all added up to 1. We could think of them as a percentage. Softmax is what makes that happen. Once we define what our model's layers are, we can say model.compile. We give it an optimizer, a loss function, and the metrics that we want to report out. The loss function is telling us how wrong it is. So it's a measure of how incorrect the model is. And so as we go through the model and run values through it, we're going to get answers. Those answers are going to be wrong. The loss function is how we measure how wrong they are. The optimizer is Adam. The optimizer is responsible for adjusting the weights and biases in the neural network to new values that are closer to the direction that the loss function tells them they should be. And we're using Adam. That's a type of stochastic gradient descent, which are words that I know how to say. I actually kind of know what they mean. It's using calculus to figure out how to move the lines up and down and adjust the slope level. And it's stochastic because you use some randomness to do that. It's gradient because you keep getting smaller and smaller, just like the vanishing gradient problem. And it's descent because you're trying to get down to that sweet spot. There's a big U-shaped thing that you're trying to find the bottom of. So you're descending along the gradient using random numbers. So, but that optimizer, Adam is doing that, and it will figure out how to adjust all the weights and biases to get closer to what the loss function says. The loss function is figuring out who to blame, and the optimizer is figuring out how to adjust the values. And so once we compile it, then we can train it. We call model.fit, And here we've got some training data and some training labels. Xtrain is the inputs. It's all the input data. It's all the yellow bubbles right here. Ytrain is all the expected outputs. So this is the thing it's going to look at and say, nope, this was the answer we should have got. Go optimize that and make it better. Batch size is 20. That means go through 20 records before we do the loss optimizer thing. Epochs is 10. That means go through the entire set of data 10 times. So we go through the data set 10 times in groups of 20. So that's what that means. Once that's done, we can evaluate the model, giving it data that we've set aside. So we got our initial data. We took 80% of it and we used it to train the model. We take 20% of it and use it to evaluate how good the model is. And evaluate, in this case with Keras, evaluate will just spit something out to the console that tells you what the loss is like and what the accuracy is like. Once we have this model, even if we don't evaluate it, we can still use it. We say model.predict and pass it in some values for X, and it will give us back a prediction. So this is actually pretty easy code for dealing with neural networks. You're just dealing, I mean, the hard part is knowing, should I use ReLU? Should I use Atom? What kind of loss function should I use? And there's not a ton of choices necessarily for certain types of problems. Like I always, for classification problems, I usually use categorical cross entropy. Atom seems to work well for most things. But there's lots of stuff to read on what to choose on the Googles and the internets. And RNN is actually just a variation of this. And so we start with the same new sequential, but instead we create an embedding layer. And that embedding layer is the thing that one-hot encodes and does that word matrix thing that we saw earlier. And we tell it, give it all the dimensions it needs. So we say, your input into your embedding is a word that is, it is going to be the dictionary size wide. The output is going to be how many embedding columns we have. So that'd be the 6 columns we had for the semantic meaning. And then the input length is how many of them you have. So this is saying how wide the input is into the embedding layer. This is saying how big the output of the embedding layer should be. This is saying how many inputs are going into our neural network. And then we add a simple RNN after that. And it needs to know the number of embedding columns as well, so that in here it can know what to expect in its inputs. And then we give it a dense output layer of 5. That'd be 5 classes, one for Shaggy, Scoob, Daphne, Velma, and Fred. And that's how we build an RNN. Same basic idea, though. We're just using different types of layers. We ready for a demo? Like, guys talked a lot. Maybe he should show us that this stuff's real. Okay. So I'll go ahead and show you my data here. Is this text big enough? Or should I embiggen it a bit more? I'm going to go ahead and embiggen it slightly. Actually, no, I'm not. There we go. So this is that data I said before. We got, each character and their line. So here's Shaggy Rogers. Like, gee whiz, shouldn't we have landed in Paris by now? That sounds like something Shaggy would say. And we just got the 5 members of Mr. Ink in here. And go all the way down to the bottom here and see there's Velma Dinkley saying, I can't find my glasses. Right? So there's our data. I have built a little script that will do all these things I talked about. And so here I read in the training data using pandas. And I do some transforming to make it a little more usable here. So I get my features, I get my labels. So this is an array of all the features. This is an array of all the labels. And then I need to encode the labels. The labels would be Daphne, Fred. It'd be the 5 members of Mr. Ink. And so I'm going to use a label encoder from scikit-learn. And then I need to one-hot encode them. So I got a 2 categorical from Keras. So I create a new encoder. I hand it the labels. It creates an encoder. If we look at the encoder, when I run this, we can get the classes out of it. It'll just give us a list of the classes, which is just the names of the 5 members of Mr. Ink. In fact, it generates here. That's what I save that out as. So there's the 5 members of Mystery Inc. And we are going to use this encoder later to decode the output. And here I just save it off. And we are also, here we are, we're taking the encoder and we're transforming the labels from strings to numbers that the model can understand. And then, so this takes the strings and turns them into 0 through 4 for the 5 members of Mystery Inc. This then turns them into one hot encoded inputs. So instead of 0 through 4, you have 5 numbers with zeros and ones, 0s and 1, 1. And so now we have one hot encoded data. Now we need to take our words and tokenize them, our lines. And so we set a max vocabulary of 10,000 words and a max line length of 150 words. So we can't do more than 150 words of text. We create a tokenizer of that size. We say, go tear through all the text and map all those numbers, all those words to numbers. Count them up, and the most common word gets number 1, and the next most common word gets number 2, all the way down to the least common word. And I have right here, word index is most common word is the. Probably should have removed stop words. U2AI, like comes up a lot. Like, what are we going to do now, Scoob? And all the way down here to the last word, which is eyeballs, which I just think is kind of a funny last word. I don't know why. So that's what our tokenizer contains, right? That's our word index. That's what it's doing. We turn our text into those sequences, into those arrays of numbers using text to sequences. We pad a bunch of zeros to the left of it because that's what we're going to do for recurrent neural networks to help reduce the impact of the vanishing gradient problem. And then I go ahead and save the word index out to a file. And then I take the data, these features and labels. This is all the data that I'm going to use to train the model. And I split them 80-20. And that's what this little line here does. Once I've split them 80-20, I can do the code that I showed you earlier on the slides, where I'm going to create an embedding layer, a sequential model, a simple RNN, and an output layer of dense. It's got a length of the number of classes, which is the 5 members. And then I compile it using Atom categorical cross entropy and metrics of accuracy. Now that it's compiled, I can train it using the fit method, and I can evaluate it. And then I can actually make some predictions. And this is a lot of code for just taking words and using those things to turn them into numbers and everything again. But the important thing is that we loop through a couple of results, and then we save our models out to disk for use with RedisAI later. So this is the code I wrote. I'm going to actually run it now, not in this terminal. Yes, in this terminal. Python build model.py. Let's go ahead and push that guy up so you can see it better. And so here it's going through the epochs in batches of 20 or 10, whatever I set it to. And you can see the accuracy is increasing and the loss is going down. And then we do evaluate, and the accuracy gets absolutely terrible and the loss gets really terrible and gets really big. And this is because I'm not a data scientist. This model is overfit. It's memorized a lot of the answers that are in the training data, and then the test data it doesn't know what to do with. The lesson in here is that as a developer, I should not brazenly go out and say, I can do machine learning. I can do data science. I need to work with the data scientist to understand how to manage this data and fix these sorts of things. With time, I could have worked with someone to fix this, but it actually works better as an object lesson for developers to not be too arrogant and assume that they can just master this. This stuff, is actually hard. But also this model works well enough for my purposes to show how I can host it. So it being a crappy model does not diminish the learning that we're having. So we can see that I did some predictions here. So we put in Jinkies, and it says it's likely said by Velma Dinkley, which it would have been. And then here's our sequence of words coming in. 153 is Jinkies. The rest of them are padded with zeros. And it gives us 80% that's Velma Dinkley. Here we got like Hang On Scoob. That's obviously Shaggy. And it got a 95.7% as Shaggy. And Roque-Raggy got a 92.99% that it was Scoob. So, and this is Roque, and that's Raggy. And then we save the files out. So this is actually making predictions. It's working for their sort of their catchphrases, but for more generic lines that anyone could say, it fumbles. And I think that's part of the reason why the model doesn't work well. So that's a little demo just showing you how the code works, and all that code's out on GitHub. You can go play with it and make it better. I'm going to talk a little bit about RedisAI so that we can understand how it works, because I'm going to then build my application on RedisAI. So RedisAI is a module that extends Redis. So modules are plugins that you can use to add capability to Redis. All this is free and open source software, so you can go out and play with it, have at it. So RedisAI adds AI capabilities to Redis. Specifically, it turns Redis into a model server. What that means is that I can take my machine learning models, deploy them to Redis, and then people can use Redis commands to invoke those models. As opposed to taking a machine learning model, putting it in their Python application and invoking it, they can put it in Redis and call it over Redis protocols, or RESP specifically, to access it from any language they want. So it lets you sort of containerize your models without containerizing your models. And of course, it's Redis, so it's fast and easy to integrate with. RedisAI lets you do multiple backends. So you can have a TensorFlow model, a PyTorch model, and an Onyx model. So if your data science team wants to change the technology, the tech stack they're using, they can swap out the models. The developers don't have to do anything different. If the developers want to use something other than Python to talk to data science models, they can. They can use JavaScript. They can use whatever language they want to. They can use, what's a good example of a language that has poor data science support? Ruby? Ruby would be a good one. What's that?
COBOL, right, Camille?
Yeah, COBOL.
What about COBOL?
Well, if you had a Redis client for COBOL, in theory, you could invoke models on RedisAI with it. I'm not aware that there's a Redis client for COBOL. We thought about having me write one just for kind of the fun of it, but I'm afraid I'm gonna get stuck doing that then.
Sorry, I've done a lot more Fortran than I have COBOL, but I wouldn't recommend that as a modern language either.
That's a fair point.
Just mention this because earlier this year I was coaching a team that was doing hybrid COBOL and data science. So.
Oh, really? That's interesting. So
Insurance industry?
Finance.
So you've probably heard of TensorFlow and PyTorch. I'm guessing a lot of people have heard, everyone's heard of TensorFlow. PyTorch is a similar thing as TensorFlow. Onyx you might not heard of. Onyx is the Open Neural Network Exchange. And it's sort of like a standard model format that you can use for lots of different platforms. And so there's tools to convert your models from TensorFlow to Onyx, and from PyTorch to Onyx, and from scikit-learn to Onyx, and from Caffe to Onyx. And so Onyx becomes this sort of standard that you can use that everything supports, which means basically you can run any model on RedisAI. RedisAI introduces two new data types, the tensor and the model. The tensor is just a multi-dimensional data structure for inputs to the model and for outputs to the model. And the model is the thing that does the actual predicting, the actual inferring. Using it's pretty simple. You load a model using the AI model set command. You load a tensor using the AI tensor set command. So now we've got a model in there. We do that once usually, right? And then we load a tensor. We tell the model to run. Tell it, use this as an input tensor and write your outputs to this tensor here. It writes it out. And then we go and read the output tensor. So that's it. Yeah. Write out my input, process, output. Right? Pattern is as older than computer science. From a Redis command line, this is how it works more in detail. We call tensor set. We give it the key that we want to store it in, the Redis key. We give it the data type that it's going to contain, which is all the favorite floating point and integers that we know and love. and we give it the dimensions, the shape. This is how wide it is in each particular dimension. This is a 2-dimensional tensor because it's got 2 values. You could have 12 values and have a 12-dimensional tensor. It doesn't matter. This has got a shape of 2 and a width of 7. That shape of 2 is for 2 classifications and 7 words. So this is us, these are our 2 things that we want to classify, the 2 bits of speech, and then it's up to 7 wide. So you see we got the padded zeros there and everything. So we pass in the shape, we pass in the values, and it sets the tensor. You can actually set it as a blob as well, programmatically. And pass in a string that represents the binary. That's not great for humans, but good for the computers. Tensor get, you just say AI tensor get, and then the key. And then you say, give me values. You can say also give me the blob. And you can also ask for metadata back. So the metadata will say, tell you the shape and the data type it contains. So these are just getting and setting tensors. To actually load a model, I'm not using the Redis CLI internally. I'm using the CLI from the command line itself. And so I'm saying Redis CLI -x. -x says, if you do Redis CLI and then a command, it will run it. If you do -x, it will run the command, but the last bit of the command will be the model, the file, the read from standard in. So what we're doing here, we're setting the model, we're putting it in a key, we're selecting a backend. Right, so our backend, TensorFlow, PyTorch, Onyx, TensorFlow Lite. We say whether we want to use the CPU or the GPU. The model determines that. And then we pass in a file that is the model from the file system. To make actually make an inference, to make a prediction, we call model run, pass in the key of the model we want to run, pass in the input tensor or tensors. You can input multiple tensors if your model supports that. And the key of the output tensor or tensors. In our case, our output's going to have 2 values. One for Shaggy and one for Velma here. One for each thing that we wanted to classify. So that's all the commands for RedisAI. Putting it all together, we can build a little application where we type in a word. We can send that off to Redis using these commands. We can, Redis will then delegate that to RedisAI. RedisAI will then delegate that to the model, which will make a prediction, write an output, return that through RedisAI, return that to Redis. And then our application can pull it back and we can find out that that was indeed Scooby who said Roke Raggy. So that's sort of RedisAI in 5 minutes. I'm going to show you now the little application that I built that is fun and ridiculous that puts this all together for this. So let me bring this back down here. So I showed you the Python code to build these models, and it actually spits out these models right here. So if we look here on the left, we got an Onyx model and a protobuf file representing the TensorFlow model. And so we could take those models, the code to save them is right here. For Onyx, it's 2 lines. You use Keras to Onyx, takes a Keras model, spits out an Onyx model, save the Onyx model to a disk. Easy peasy. To get it to work with TensorFlow is a little more involved because we have to freeze the graph and do a bunch of things that I don't really understand, but I know that it works, and I know that I like using Onyx better, honestly, because it's easier, and I'm a developer. I have built a simple node application that will load these models, and let's see if I can find the code here. It's at server.js. And it just goes through and uses a library called IO-Redis to talk to Redis. And we go through and we load up our models. Here's our call to AI model set to load the Onyx model. This loads the TensorFlow model. That word index, we saved that off so that we could use it in our application because we need to turn our words into numbers. And that classes file we saved as well, because we need to turn our outputs into classes that we can use to display something. We don't want just numbers, we want classes. And this is just using a little Express backend. And so our one request that comes in, we pass whether we're going to use Onyx or TensorFlow. And then this is actually, I think, kind of the most fun line of code, because this is taking the line of text and turning it into the numbers that are going to be input into this model. And so we lowercase it all, and then I use a couple of regular expressions to get rid of anything that aren't letters or numbers, and to make sure that we only have one character white space between each word, not multiple characters. And then I trim everything off the edges, split the words on space, and then I just map the word, looking it up in that word index. And so that word index is going to take like the and turn it into one, and it's take eyeballs and turn it into 2,100 and whatever it was. And if there's words it doesn't recognize, it's going to return them into undefined. And so this last thing says, well, if the index is undefined, and undefined is falsy, then it's 0. Otherwise, it's the index. So that just replaces all the undefineds with zeros. That's all this is doing.
Guy, did someone code review this? You're evil.
Shut up, Joel.
This doesn't pass the 2 a.m. drunk contest. This doesn't pass the 9 p.m. drunk contest.
Yeah. So one of the things that I try to do is when I write code for production, it's very different from how I write code for teaching how tooling works. And so having just sort of this linear thing that I can scroll through is easier to talk through with lots of comments. So
just give you a hard time.
I know. That's why I told you to shut up. So and then we pad it and everything, just like we did before. We call AI tensor set to set our tensor. We run the appropriate model, Onyx or TensorFlow, and then we call tensor get to get the value back out, and then we display the results. And so on the front end, I've got a really boring app.js, which is 60 lines of code. It just basically hits a REST endpoint. It's not even REST. It's just RCP over HTTP, right? It's not actual proper REST that goes out and hits this little URL. So let's run it. So over here, we need to get RedisAI up and running first. So I've got a little shell script that I use to do that. It goes ahead and runs RedisAI from Docker with all the appropriate settings. And then we can go ahead and start up our server for our inference server. So that'd be npm start, and that will run server.js. And then on my third terminal, I'm going to launch the web client. And I'm going to use, if you haven't seen this trick, this is great. Do python -m http.server, and it creates a web server in that directory. This one works with Python 3. It doesn't work with Python 2. There's another command for Python 2.x. But for Python 3.x, which is the one you should be using because Python 2 is bad and evil and old, and we don't use it anymore, this will work. And so this creates a web server in this folder. So now we've got a web server in this folder. I got another web server that's handling the REST call. And then we got Redis up and running. So if we go to our browser here and I refresh this, we can see that indeed we have a web page here, and we can type a line from Scooby-Doo and it will tell us who said it. What should we type? Jinkies, maybe? We'll do Jinkies. And indeed, that is Velma Dinkley. And we can do things like, what are we gonna do now, Scoob? That would be Shaggy, right? And it can take words that it doesn't recognize. So let's I see a SpongeBob background there for Scott, so we'll do a SpongeBob crossover. Like, are we goofy goobers, Scoob? I'm pretty sure the word goofy might be in there, but goober probably isn't. And it still figures out that that's Shaggy, because that's the kind of thing Shaggy would say. We can say, I can't be seen without my glasses. That's Velma, right? So it doesn't work too bad, actually, for being as only having a 44% accuracy based on the evaluation. However, if you do something like this, And it should be, I can't see without my glasses. I can't BC without my glasses. Just to be complete there. Make sure that still says Velma. Now, if we add the comma Scoob, it thinks Shaggy said it. And this is that vanishing gradient problem that I was talking about earlier, right? This last word is just as important as all the previous words.
Well, I was going to ask you, like, what if Scoob comes first, right? Is it weighed less?
Yes.
So this will probably be.
And that says Velma. And it's because the word Scoob is, so glass is half of the determination. My is 25%. This is 12.5%. This is 6 1/4, 3 1/8, whatever half of that again is. And so things more to the left are less important. And so right? Like Scoob. What are we going to do about my glasses? That's probably going to come out as Velma. And it does. What are we going to do about Velma's glasses? Still comes out. So this is that vanishing gradient problem manifesting. But, you know, all things considered, given that this is rubber bands and hot glue, I'm kind of happy with it. It gets their catchphrases if I do let's split up. No, actually, hey gang, let's split up. Figures out that's Fred. It doesn't do that well with Daphne. Like her catchphrase is Jeepers, and it doesn't attribute it to her. And I think it's because Daphne has, she doesn't have as many catchphrases, and I don't think she really has as many lines. Like Shaggy and Scooby have more lines than everyone else. And one of the things I didn't do with the data, because I'm not a data scientist, and a data scientist would tell you should do this, is you should balance the data and remove some of the examples so that there's an equal number of Shags and Scoobs and Velmas and Daphnes and Freds in your data set. Otherwise, it'll be biased towards predicting one or the other.
Diversity, yeah.
Yeah. But that's my little example. If we go out and look at the command line for the little node server I wrote, it's actually spitting out all these answers. So that last one we did was, it was only 53% sure that was Shaggy. So it wasn't very sure. And then, but Daphne was in the middle. And so, you know, if we go ahead and say, Jeepers, they mean business, that's something that will come up as Daphne. So, and we can see here that it's fairly certain. But so this thing spits out sort of the score. So that's my fun little demo. You are welcome to go play with it and pull that code down and make all this stuff work and make it better and do all those things. We've covered a lot of stuff. Neural networks, recurrent neural networks, Keras, and Redis. I've got a bunch of links here if you want to go check some stuff out. You know, if you want to check out RedisAI, it's redisai.io. Yeah, Redis itself can be got at redis.io. This is a Docker image you can use if you like the Docker thing. And all of my code is right out here, so go check that out. I've got, you know, I work for Redis Labs, obviously. We have a Discord server. Go join our Discord server. I'm always on there. If you have Redis questions, you can ask me or another member of the team. Lots of people are there to help. We offer free Redis classes at Redis University. So go sign up for free schooling. And we got a bunch of videos out on our Redis University YouTube channel, including 2 on RedisAI that I've recorded relatively recently, and a 3rd one on its way. So if you want to go a little bit deeper and learn a little bit more, and you don't have to get that one slide. This is the only slide you need to get all the stuff. This has the link to my GitHub repository, which has the slides and the code and my talk abstract and all those things. You can just use this QR code, which will never give you up, nor will it let you down. It's not going to run around or hurt you. It will actually take you to my GitHub repository. So that's pretty much all I got. Give me a
Cool,
follow
Guy.
on Twitter, please. And thanks.